Welcome. In today's class, we will revise and summarize what all we have learnt about the statistical thermodynamics of ideal gases, where as you have seen that we are mainly focusing on gases which are comprised of atoms such as helium or argon, or diatomic molecules such as carbon monoxide, nitric oxide, HCl or HBr, which can be classified as heteronuclear diatomic molecules, or gases like hydrogen, deuterium, oxygen, etc., which can be clubbed under the common name of homonuclear diatomic molecules. And we have already seen that the microscopic information regarding any of these systems is actually collected and contained in what is known as the canonical partition function. So, what is this canonical partition function? If you maintain the ideal gas at a given temperature, volume and with a constant number of particles, either atoms or molecules, in that case, if you start from the Hamiltonian of the system, you can write down all informations regarding the underlying accessible microscopic states along with their associated probabilities in the form of this canonical partition function. And as shown here, this is what the expression for this canonical partition function is. So, as you see, in addition to depending on this capital N, the number of particles, it depends on the small q, that is the single particle partition function. And we know that for monatomic ideal gases, small q will derive contributions from the overall translational motion of the atom and the underlying electronic and nuclear structure for a monatomic ideal gas. Whereas, if you have a diatomic ideal gas, then two additional terms will come into the picture, which are due to the rotation of the molecule about an axis and also the vibration of the chemical bond that is connecting the two atoms that are constituting the molecule of the gas. And we have discussed in detail like how we can calculate each of these quantities given the situation. And in general, we know that if we know the thermodynamic quantities like V, T and the number of particles, in that case we are able to find out Q trans, Q electronic, Q nuclear, provided you have information regarding the microscopic structure in terms of the underlying energy states of the electronic and nuclear nature, and also the transition energy between the first and the ground and the first excited electronic state. With this background in mind, then we have already talked about how to obtain the thermodynamics from the canonical partition function. And as you know that all the thermodynamic properties that are of interest in our case can be derived if you know the dependence of ln q on properties like temperature, volume or the number of particles. So, with this background in mind, what we have also pointed out that the underlying structure plays an important role in overall thermodynamics. That is because the presence of this underlying structure gives additional corrections. So, corrections that add up to the dominant term in each of these thermodynamic properties. And we have seen that in the case of monatomic ideal gas, simply because we can partition the overall single particle canonical partition function into the contribution from the center of mass, that is structureless, and the internal structure, all the thermodynamic properties that we could derive, they also had explicit contributions arising from these three factors, which added together to give us the net thermodynamic property. Now, if we look at what happens in the case of the monatomic ideal gases, in the case of the diatomic ideal gases, what we find is, in this case, because of the presence of these two extra terms that you see here, there are two extra terms which are appearing in all the thermodynamic properties, which can be attributed to the effect of discrete energy levels present at the present for the rotational and the vibrational degrees of freedom for the diatomic case. And as a result, we would say that, well, the presence of these two extra terms, for example, Q dot, gives the corresponding extra terms in each of the thermodynamic properties that we have shown here. Similarly, the presence of Q vibe leads to this vibrational contribution to each of the thermodynamic properties that we see. Now, we have seen all that, and now let us try and understand what happens if I want to derive the ideal gas equation starting from the canonical partition function. Now, we have already seen in the last lecture that the pressure is related to the derivative of ln Q with respect to volume, keeping temperature and the number of particles constant. Now, if I think about what the structure of small q on which this capital Q depends, we find that in both the cases the explicit volume dependence of the small q term comes through this translational partition function. So, in the case of the monatomic ideal gas, this corresponds to the translational motion of the single atom in the given box, and here it corresponds to the translational motion of the molecule as a whole, represented in terms of the translational motion of the center of mass in the confining volume under the given condition of temperature. Now, what we find here is it's possible then to write down what the Q trans is, irrespective of whether we are dealing with a monatomic ideal gas or a diatomic ideal gas, and this is given in terms of the volume of the gas divided by the cube of the thermal de Broglie wavelength lambda, where we have already seen that the thermal de Broglie wavelength lambda depends on temperature and the mass of each particle, and therefore, the way the monatomic and the diatomic gases will differ from each other will be in terms of this quantity m. Now, if we use this, then taking a natural logarithm of Q trans and then estimating the derivative directly gave us the pressure in terms of n kBT by V. We have already done this derivation. So, what I wanted to emphasize over here is that the pressure that here when I derive the pressure, the result that I get, this is the same as far as the monatomic ideal gas or the diatomic ideal gas is concerned, and that is because both of them have identical terms giving rise to the corresponding to the translational motion in the volume V, and therefore, I would expect that the pressure term that I see here would be n kBT by V. In both the cases, irrespective of whether I am looking at the translational motion of an atom or the translational motion of a diatomic molecule. Similarly, we have also checked if the theoretical development that I have been presenting here for molecular thermodynamics of ideal gases can reproduce the known form of chemical potential of an ideal gas, where we know that if I want to predict what the chemical potential of the ideal gas is going to be at a given temperature and pressure, this is dependent on what the chemical potential of the gas is at a temperature T under standard conditions of 1 bar pressure, plus an additional term that depends on the pressure at which I am going to observe the chemical potential of the ideal gas. Now, we have already carried out this derivation, and indeed we have been able to show that starting from the definition of chemical potential in terms of ln capital Q, then it is possible to find out what exactly the form of chemical potential would be in terms of the parameters like mass of each particle, temperature, then q electronic, q nuclear, etc. Now, here what once again I would like to highlight is that this expression has given me one set of terms that is independent of pressure and dependent on temperature only, and it also depends on the kind of system that we are working on. So, very easily I can say that this must be the chemical potential at 1 bar pressure at a given temperature T. So, when I have 1 bar pressure, by definition this small p is p by p naught, and p naught where p naught is the standard pressure of 1 by 1 bar. Therefore, I put this equal to 0. So, this must be the mu naught. Okay. Now, what I have here is this additional term k b t l n p, which reproduces correctly the form that I expected from our prior knowledge of thermodynamics. We also looked at the predictions of the internal energy for an ideal gas and compared the predictions of our theory that we are presenting here with what we know from, for example, equipartition theorem or Joule's law. And here what we found is that for a monatomic ideal gas in the like helium, if you know the underlying microscopic structure and the energy values associated, it is found that at not too high temperatures, the internal energy of the system is essentially corresponding to the translational energy, and at low temperatures the correction terms appearing because of the underlying electronic structure is negligibly small. But if you go to very high temperatures, then what you will find is, you will find that the contributions from this correction terms appearing because of the underlying microscopic structure of the gas is becoming significant. So, as you understand that if you go for temperatures like 1500 Kelvin or 2000 Kelvin, this number is going to become larger and larger and will start competing at very large temperatures with the translational contribution. So, basically the message here is as follows. If we are at a few hundreds of Kelvin, in that case the internal energy of the gas is dominated by the translational energy, translational contribution to the internal energy. And the translational contribution, as we have seen here, this is dependent on kT, right, and therefore, and there is no other dependence in here, like volume does not appear. Therefore, u is a function of temperature and temperature only. It is only at very high temperature that we start seeing an additional correction term in the form of u electronic, but at normal temperatures a few hundred of Kelvin, these correction terms are not important, and therefore, whatever experiments that we do are good enough to be explained with the equipartition theorem. With this background in mind, let us now go ahead and try and talk about this property, the entropy of an ideal gas. The way we will calculate this quantity is, at this point we know what u is, what f is in terms of ln q from ln q. So, S is equal to u minus f divided by t. A few lectures back I asked you to work this out, and this would be the expression for entropy as calculated starting from the current model of the canonical partition function for this monatomic ideal gas. And here what we find is this S electronic. This is a term which is a correction to the big term that you see here, that depends on the underlying electronic structure of the atom. As you can see very well, all the terms that are appearing here, they are connected to Q trans, that is, they are connected to the contribution to entropy from the translational motion of the atom in the box, and this is the contribution from the underlying electronic structure. And this equation is known as the Sackur-Tetrode equation. And in today's class, we are going to use this equation a lot, and so it is very important that we understand what are the different quantities that are involved. Let me write down explicitly what S electronic is. What you must note over here is that in this particular expression, I have S electronic is proportional to n kb, because this appears as a prefactor for both the terms that you see here. Okay. Now, then I have two terms, all of which depends on parameters that are associated with the electronic structure of the atom present in the system, and of course, its temperature dependence comes through the appearance of beta. Now, once I understand what S electronic is, I find that in order to be able to use the Sackur-Tetrode equation, I would like to simplify it a little bit, and this is what I shall be doing. As I understand that instead of writing out specifically the total expression for the entropy, I can very easily write down the entropy as V by lambda cubed into e to the power of 5 by 2 divided by n, this plus S electronic as I have shown here. So, what is lambda? Lambda square by definition is equal to h square divided by 2 pi m k t, and in the slide that I was showing to you, I had this net expression put in here instead of lambda cube. Now, if I go back and try to see that, well, I have V and I have N. So, what happens if I introduce this quantity small n, which is capital N divided by V? If that is so, then I can rewrite the expression of S as n k b ln e to the power of 5 by 2 plus n k b ln 1 by lambda cube into 1 divided by n by v. If that is so, then S turns out to be nothing but 5 by 2 n k b minus n k b ln small n into lambda cubed. So, what I have done is I understand that whatever I see here appears in the denominator. So, when I take it up, a negative sign comes over here because I have a logarithm here, and therefore, I can very easily say that capital S in this case, and of course, you have this plus S electronic. So, that is n k b multiplied by 5 by 2 minus ln n lambda cube plus S electronic, right. So, as you see, then an alternative and simpler form of the Sackur-Tetrode equation involves this number density n and the thermal de Broglie wavelength lambda. We are going to use this equation now to do some of the following checks. So, first we are going to check for the accuracy of the theoretical prediction of entropy of an ideal gas, first by examining whether the entropy that we are calculating here preserves the extensivity of entropy as denoted by the basic formulation of thermodynamics. We are also going to check if the current formalism given in terms of the Sackur-Tetrode equation can correctly predict what would happen when I mix two ideal gases irreversibly or reversibly. And finally, it is possible to estimate the absolute value of entropy using the Sackur-Tetrode equation. If you know which thermodynamic state your system is present, in that case you can use these theoretical estimates and compare them with experimental results, which will tell you whether the theoretical prediction that you are making using the formalism of molecular thermodynamics is correct or not. So, let us take each of these one by one. So, the first thing that we check is the extensive nature of calculated entropy. So, the first thing that I do is, in order to do this, all the time we understand that if there is a property x which is an extensive property, in that case it must be a function of capital N in such a way that if I replace n by n prime and n prime is equal to 2n, then x will be replaced by x prime such that x prime would be equal to 2x. So, that is the basic definition of an extensive property. And here we know from basic thermodynamics that entropy is an extensive property, and we have used molecular thermodynamics to find out some expression for entropy. Now, we are going to test if the expression that we have obtained for entropy in terms of the Sackur-Tetrode equation correctly tells me that if I replace n by 2n, or in other words, if I replace n by n prime such that n prime is equal to 2n, if I have done everything correctly, then if the Sackur-Tetrode equation is correct, then the entropy should become twice of its original value. So, in order to do this, what we do is, if this is the expression for S, then what we do is we write down the expression for S prime, where in case while calculating S prime, I am replacing n by n prime. Obviously, the number density small n is represented by small n prime, and S electronic, this is also becoming S prime electronic. Now, if you would remember that S electronic is a term that is n kb into one particular sum plus another particular sum, and these two do not depend on n. So, in S electronic, if I replace n by n prime, so S prime electronic will now become n prime kb into the same x1 plus x2, correct. So, if that happens, then what I can do is I can now go ahead and replace n prime by 2n and check what is small n prime and S prime electronic is. I realize over here that when I put n equal to n prime, or n prime equal to 2n, the other extensive property that I have in this expression is volume. Then volume goes from a value of v to v prime, where v prime is equal to 2v. Now, let us check what happens to the ratio n by v. As I understand that n by v is equal to n prime by v prime under this condition, and therefore, I should be able to say that, well, the number density is not an extensive function. It remains the same even if I replace n by twice its value. Now, if I put this back, so I understand that here n prime is 2n, capital N prime is 2n, small n prime is nothing but small n, and S prime electronic is nothing but 2 into S electronic, and therefore, this is the expression that we would get here. And if I now compare the expression for S prime to the expression for S, that is the entropy, we immediately conclude that S prime is equal to 2S. So, as expected, the Sackur-Tetrode equation correctly preserves the extensive property of entropy as derived through the prescriptions of molecular thermodynamics. Now, if I look a little closely enough, I understand that this entire analysis depends very much on the presence of this factor capital N here. Okay. Now, where did this factor capital N come from? if we go back and look at the derivation, we will find that incorporation of this factor n factorial in the expression for capital Q is the reason why in the final expression of S the term capital N appeared here. Now, what would have happened if we just did not write down this n factorial? We just wrote capital Q is equal to small q to the power of n, which means that the corresponding expression for entropy would have been given by something like this. Now, what would have happened if you wanted to check for the extensivity property of entropy? You would replace n by 2n. Here also you will replace n by 2n and you will replace v by 2v, and then S prime will turn out to be 2n kb ln 2 pi m kbt by h square to the power of 3 by 2 into 2v into e to the power of 5 by 2 plus 2n kb S electronic. So, immediately you can see S prime is not equal to S, and that is because there will be an extra ln 2 term here that will destroy the equality, and therefore, we have made everything correct by incorporating this term n here, which in turn was introduced in this picture by the famous scientist Gibbs, who pointed out that, well, unless and until you are having this factorial n, then you are not going to get the correct thermodynamic properties. The other reason why Gibbs wanted to introduce this n factorial is that obviously, unless you do so, you are not taking into account of the fact that you have identical particles constituting the gas. Okay, we have already discussed it many times that in order to avoid overcounting of entropy, overcounting of the microscopic states of a system, we should be dividing by n factorial in the case where I have identical particles. Now, let us next have a look at the entropy of mixing of ideal gases, and here also we are going to use the Sackur-Tetrode equation and check if the Sackur-Tetrode equation can explain the entropy of mixing of ideal gases correctly. Now, the first case that we think about is the irreversible free expansion of an ideal gas that are comprised of capital N particles. So, we are basically looking at the situation where my initial system is something like this. So, I have a partition separating the entire volume into two equal volumes, V on this side and V on the other side, and this part is evacuated. So, if I now withdraw this partition, the gas will undergo a free expansion, which is an irreversible expansion, and the final volume of the gas is going to be 2V. Now, in this particular case, what we have to consider the fact that in the initial state, the number density is capital N particles present in a volume V of the gas, of the blue gas, and therefore, the initial number density is N by V. So, using the Sackur-Tetrode equation, I can write down the entropy of the system in the initial equilibrium state. Now, what is the entropy of the system in the final equilibrium state? So, for that I will have to know the final number density of the gas. Here I have now capital N particles occupying a volume of 2V. Therefore, I see that the number density has halved, and if I put it back here, and since this is essentially Joule's experiment where the temperature remains constant, I can argue that the lambda values are going to remain the same, and within the temperature range that we are talking about, S electronic changes, let us assume that they are going to be very, very small. Now, what do you expect? we have already seen that under such circumstances, from thermodynamics we expect an increase in entropy. And by Sackur-Tetrode equation, if I use it, I find that delta S is n kb ln 2, which is a positive number and therefore correctly predicts the increase in entropy when I allow the ideal gas to undergo an irreversible free expansion, which anyway takes place under isothermal condition. Now, if I have two different gases on two sides of the partition, if I withdraw the partition, it is as far as the yellow gas is concerned, there was no yellow gas on the other side of the partition. So, it is an irreversible free expansion of the yellow gas, just like the irreversible free expansion for the blue gas. And therefore, for each ideal gas, I can once again repeat the same argument, and therefore, I should be able to say that, well, here the change in entropy is going to be positive, and it is going to be twice the amount of what we have seen from the case 1, and that is correctly predicted by the Sackur-Tetrode equation. So, this brings us to the final and most interesting case, and this is a case of reversible mixing of two identical ideal gases. So, what is it that we are trying to do here? I have in the initial equilibrium state the same gas on both sides of the partition, and I reversibly withdraw the partition separating the two halves of the box. Now, what will happen? What do you expect? Since both the gases are the same and you have not done anything from outside other than just removing the partition, you do expect that there should not be any change in entropy, or in other words, delta S is going to be 0. Now, let us see what is predicted by the Sackur-Tetrode equation. We find that the initial state, I have capital N particles of the ideal gas on this side and capital N particles of the gas on the other side, and therefore, I have a total of 2 N particles of the blue type present in a volume of 2 V. Therefore, the initial number density is N by V, and accordingly the initial entropy of the system is given by this. Now, when I allow the reversible mixing under isothermal condition, what is the final density? The final number density once again is N by V, and therefore, Sackur-Tetrode equation correctly predicts that the delta S in such case is going to be equal to 0. And therefore, you once again see the importance of the appearance of the capital N term inside the log, and unless you have that correction, it is not possible to reproduce all these informations. And finally, if one compares the estimated values of entropy as obtained from the Sackur-Tetrode equation to the ones obtained experimentally, as you can very well see from the data presented here, that there is an astonishing agreement between the theoretical prediction and the experimental results. So, this brings us to the conclusion that the formalism that we have proposed through the molecular thermodynamics or statistical thermodynamics is actually an accurate one. It not only gives us a molecular derivation of the ideal gas law, the form of chemical potential of an ideal gas, or why the temperature dependent term, why the internal energy will be dominated by a term proportional to temperature at normal temperatures. It is also capable of reproducing the essential properties of entropy of an ideal gas, and it agrees very well with the experimental data. So, that for any theoretical framework is an enormous achievement, and in the next class we will see how these considerations can be extended to understand the properties of diatomic gases, ideal gases, where the structure is also playing, underlying structure is also playing an important role by having this additional contribution of rotational and vibrational structure. Thank you.